So before we move on, I first need to introduce you to pseudocode and truth tables. We're going to be using both of these tools throughout the next part of this course. So what is pseudocode? Maybe you've heard of this, or maybe this is a new term to you. So let's not assume that you know what this is, and let's just go ahead and dive into it. It's a written way to express logic. Now there's code and there's logic. Logic deals with logical problem solving. It's very verbose. It's human readable. And it's going to help you to visualize for the problem solving process. All right, so let's take an example of pseudocode. We've seen this in the last topic. We have a switch and we have a light. Now I've added labels to the top of these. So the switch is switch 1 and the light is light 1. Now, how would you express this? What I want you to think about is the power flow. So if you were walking through this process and trying to express why the light is on in this case, how would you do that? So let's go ahead and walk through the thought process before I show it to you. So here we have power, right? We have the voltage coming in. We have a switch. And what state is this switch in? It's in an on state, right? And then we move across and we have a light, and the light bulb is turned on. So therefore, how could we express the conditions that led to this light being turned on? Think about that. If you were trying to explain this to someone there in your home or your business, how would you explain this to them? You would say something like, if switch 1 is on, right? So if this is on, then light 1 is on. And see how verbose this is? It's in a very human readable format. You're expressing the logic of this particular circuit. So let's try it in its opposite state. So here we have it. The switch now is in what state? It's off. And notice that because of that, the light is also off. Therefore, there's a cause and effect. So let's walk through the logical process here. If switch 1 is off, then light 1 is off. Okay, does that make sense to you? All right, now let's go one more step. How can we combine both of these expressions, how we just verbalized it, how can we combine that down and condense it into just one expression that allows us to be able to visualize how this circuit works in all the different states? In this case, it's only 2 states, right? On or off. Think about that. What's common here? Let's go and let's look. We have an if, right? Here's an if. We have a then. So therefore, we're checking if this, then that. Right? This is the cause. This is the effect. The if is the cause. The then is the effect. All right? What else is common? We have switch 1. And notice that it's in the if statement. And we go across and we say, we're checking the state. So is on or is off. Okay. So therefore, just by looking at the circuit, we can determine, what if we scratch that off of there? And we just say, if switch 1, then light 1. Let's try that. So if, and notice that I just put the parentheses around. So I'm going to capture all of the causes within the parentheses, because right now we only have one, but what if we have a bunch of them? What if we have a bunch of switches and it affects the light? Therefore, we'd want to capture all of those. So we'd want to put them in parentheses so that we could see the different states. Some might be in series, some might be in parallel. So therefore, you want to group them. So let's go ahead and put that in. If switch 1. Now, just by looking at this, once you get used to this process, you'll go, oh, okay, so if it's on, then do this. If it's off, oh, then no, that has an opposite effect. Then light 1. And the way you actually would express light 1 is to put these little parentheses after it. And you don't necessarily right now need to know that that actually is a function. So we're going to cover that in the computation course. But for right now, all I want you to do is wrap your mind around how you walk through the process of pseudocode. And if you can read this, you would go if, and you would know that this is going to give you a true or false condition, a 1 or 0 on and off condition. And the way that this works is if this whole expression within the parentheses is true, right? Then this will be true. It will go ahead and turn on the light. If this evaluates is what we call it, all of the states within the parentheses evaluates to a false. Like here, it's false, right? It's off. So therefore, it's going to be false. So if false, here's what's going to happen. And just accept this for now until we get into the computation course. The then is not going to evaluate. And that's why the light stays off. All right, so if you just frame yourself, sit right here, spend a little time, understand what I just walked through. This is really going to set you up to be able to know how to program and think in logical problem-solving steps. Let's go to the next one. What is a truth table? Okay, so we've got pseudocode, and then we have a truth table. It's actually a logic table. All right, so pseudocode is expressing in a logical way, and this is also expressing in a logical way. It's a logic table. It shows the state, true or false, for the given arguments. Well, it's a truth table. It's going to build your logical thought processes, and it's going to help you to visualize for problem solving. All right, so if you've got a set of problems in front of you, you can break those down into both pseudocode and truth tables to be able to figure out what's happening there. Let's walk through a truth table. You ready? All right, so this is the beginning state of a truth table. So we have a switch and a light bulb. We just saw this circuit. Now, what can we say about that switch? Because it's on, that also means the same thing as true. And it also means the same thing as 1. So on, true, and 1 are all the same thing. So therefore, in a truth table, what we actually use is the 1. All right, so they're just states. And that's what we're trying to capture here is the state. So if that switch is on, which is a 1, then the light bulb is in what state? It's on, so therefore it's true, and it also has a 1 state. So let's put that over there. Now let's do the opposite one. So here we have the opposite state. We just went through that in the pseudocode. So now that switch is false, it's off, it's false, and it's also 0. So let's put the 0 there. See it? Okay, so if the switch is false, then the light bulb is false, off, and 0. So let's put that 0 there. What does this truth table tell you? If all that I showed you was this truth table, how could you read that? Think about it. Let's say I hide this and I don't give you that circuit. You could look at this truth table and you could say, all right, if the switch is set to a 1 or it's on, then the light bulb is going to be on. If the switch is off, then the light bulb is off. We have a cause and effect, right? Let's move on. Let's do multiple switches this time. All right, so notice that I have switch 1, switch 2, and then a light bulb, which is an output. So I have input 1, input 2, and an output. Here we go. Now the key to this is you have to list out every single state. So now I have 2 switches and a light. So if I have two switches, how many states will I have? How many separate conditions for this circuit will I have? Each switch has two states. I have two switches, so therefore I have 4 different combinations here. All right, so let's walk through them. Switch 1 is in what condition right now? What state is it in? It's a 1. Switch 2 is in what state? It's a 1. So therefore, the light bulb output is also a 1. Therefore, you would read this as if switch 1 and switch 2 are both on, then this light is going to be on. This output will be on. Let's do another one. Ready? Now see if you can fill this one out yourself. So switch 1 is 0, switch 2 is 1, and therefore the light is off. Now maybe I should explain this to you real quick. We're going to go through this particular circuit when we get to the AND gate. However, what you see are 2 switches in series. So therefore, how does power flow? Goes through the switch and it says, oh, that one is open, so I can't get through. So let's come up here to this one. So this one is on. So I would go through this switch and it's on, so therefore I could flow through it. Yep, I can get through that guy. I'm going to go over here to this one and I'm going to say, yep, you're also on. Because they're in series, now I can flow through to the light and go to ground. That's why the light comes on. So that's how this works, because they're in series. All right, let's do the next one. Ready? Okay, you do this one. What should the truth table be? Switch 1 is 1. Switch 2 is off. And the light bulb is off. What's the last one that we should have here? So I've got a state of 2 of them being on, and then 2 states of them being opposite of each other. So what's the next one? There's one more state left. They're both off. So if they're both off, then it would be 0, 0, 0. Now look at your truth table. From this tool, this table has a logical thought to it. You can see switch 1 and switch 2 are both on, then the light is on. If switch 1 is off, switch 2 is on, then the light is off. See how you can just read this and you quickly know not only the circuit, but you also know the code. You can sit down and you can map out pseudocode from this. You can say if switch 1 and switch 2, then light 1. Now, there is a more universally accepted condensed version of the truth table. So I'm giving you the more verbose way of doing it and the globally accepted way of seeing a truth table. So this is the one that we just did. It's much more verbose. So this is the more accepted truth table format. It's a condensed version format. This can get pretty lengthy depending upon how many inputs you have. So let's look at this one over here. This X would actually describe the circuit. So later you'll see that we will be filling this in. For now, we're just going to call it X. Don't worry about it. This first row represents the states of the first input. So this would be switch 1, when it's off or when it's on. The first column represents switch 2, switch 2. So I got switch 1 is the row, switch 2 is the column. Everything in between here is the output. So if I'm down here and I say, here's switch 1, here's switch 2, and they're both off. See if you can figure out what the output is. Yes, you know it's 0. You would go switch 1, come down to switch 2. That state is also off, and right there is the output of the light. All right, now I'm going to give you one on your own to do. Ready? Switch 1 is on. Switch 2 is off. What's the output? Right there. So you would go, this is switch 1, and I would come down the column until I got to the state of switch 2, which I said was off. And so therefore the expected output would be off. If both switches are on, I would go, okay, here's switch 1. I'd come down and I'd say, oh, well, there's switch 2. So therefore the output would be on. This is the truth table you'll see more often. But I want to give you both versions. That way you can get comfortable with both of them. This one, I think, helps you to see it easier. It's much more verbose. However, get used to also seeing it in the more condensed version. All right, so what are the takeaways? Pseudocode is a verbose, human-readable expression of logic. The truth table provides the expected state of the output for the given arguments. And arguments here would be the inputs. You can also look at arguments when you get into pseudocode. So that's why we just use the word arguments. Okay, just get used to seeing that word. You'll see it a lot when you get into programming and into code. Both tools build logical and analytical thought processes. You could see how walking through those tables, you're thinking in a logical sense. And you're getting that analytical process because you're problem solving. So therefore, they both help you to visualize for problem solving.